morning, everyone. Thank you for joining us. We can just now start with a short introduction of the webinar in the meantime that other people join us. First of all, I would like to thank you all to be here. This EHPA webinar on the topic From Waste to Worth, Innovative Waste Heat Recovery Solution in District Heating and Cooling, where we are going to present you some demo cases from EU-funded and not EU-funded project on waste heat recovery and in the district heating. First, to go deeper into the agenda of the webinar, I would like to show you some housekeeping rules. And as you can see, you cannot activate your microphone, neither your camera during the webinar, but we encourage you to write down your answer in your question, in the chat, both during the webinar and during the Q&A section. Just please remember to also write down the name of the speaker you're addressing the question to in the chat. You can do it both during the presentation as well as the end of the session. Let me shortly briefly show you the agenda. After this brief introduction, we will have an opening statement from Andras Takacs from Hero Heat and Power that will talk about the role of district heating and cooling in the current Fit for 55 framework. And for that, we will go more into the technical aspect of waste heat recovery in district heating with the presentation of 4 different demo cases from 3 European-funded projects and 1 national project with Combissul from EDF that will present the rewarded La Seine-sur-Mer demo case, and Hugh Moore from Glade Gateway that will present the demo cases of the 2Grid and other EU-funded project, and John Summer from We District project that will talk about the data center as energy preserver. Last but not least, Jere Oksanen will talk about the Helsinki National District Heating Project. At the end, we will have half an hour of Q&A section where all the speakers will answer your question both in the chat and during the last minutes of the webinar. As you know, this webinar is organized in the framework of Rewarded project. Rewarded is an Horizon 2020 project started in 2019 that will last until the end of September this year. So this is the last year of the project. And the overall objective of the project is to demonstrate a new generation of low temperature district heating and cooling network, which has been recover low grade renewable and waste heat available at low temperature. But I don't want to steal more time to our speakers, so I will now let the floor to Andras Takacs, that is from Euroheat and Power, and will show you the role of district heating and cooling in the Fit for 55 framework. After finishing his environmental engineer studies, Andras joined the Green Group at the European Parliament, where he'd work with the ITRE Industry Research and Energy Committee on energy and industry policy for 1 year and a half. And 2 years ago, he joined Euroheat and Power, our policy advisor, focusing in particular on EU legislation on renewables and waste heat sources, building and energy efficiency. Thank you to be here, Andras. Please, you can take control of the presentation. The floor is yours.
Thank you very much for inviting me. Good morning. Yes, so as you said, I'm going to speak about the EU legislations regarding waste heat in connection with district heating and cooling networks. And my name is Andras Takacs. I'm the policy advisor of Euroheat and Power, which is an international association for sustainable district heating and cooling. We have more than 150 members, national associations, research centers, but also companies. And a little bit about district heating network for those who doesn't know what's that. District heating is a centralized heating solution which can harness different energy sources. We can harness ambient heat from rivers and water bodies, but we can also harness renewable heat sources like geothermal, solar thermal, and bioenergy. And then together with heat pumps, we can harness waste heat, which I'll cover more broadly later. Then also power to heat. So for example, when there is a lot of renewable electricity with e-boilers and large-scale heat pumps, we can use electricity to produce heat. There are more than 17,000 networks in Europe. We serve 67 million EU citizens, which is the 13% of the EU heat market. And our networks in EU have 41% renewable and waste heat share. Recently, we published a study which was made by Aalborg University to map what will be the future heat source potential, what district heating and cooling networks could use. And you can see all of these sources except the deep geothermal is waste heat. This also includes industrial waste heat, but also from services. For example, the largest service is from wastewater treatment plants, so sewage water. Then we have the second one, data centers and electrolyzers, the third. And based on this Aalborg study, we found that all of these sources could produce more heat than EU will need for its heat demand by 2050. And if we are looking a bit more in detail about the waste heat potential in urban sources, so urban waste heat, then we see the same information from different sources. This has been confirmed that sewage water is the biggest share, data centers and other waste heat sources which are in an urban environment and they are easily available for district heating and cooling networks to be harnessed. All of these different waste heat sources produce different heat temperatures, and their availability also differs. The big benefit of wastewater treatment plants is that they produce constantly same temperature waste heat, also data centers, while other sources sometimes they are variable. And here we also have data which heat pump should the district heating network use to harness these waste heat. It could be air to water and also liquid to water or water to water heat pump. Since the publication of the Fit for 55 package in mid 2021, it's nearly 3 years ago, but finally we see that the Fit for 55 package introduced many good legislations which will together help to decarbonize the heating and cooling sector. So I'm going to look into more detail of these legislations which were recently adopted. One of the biggest change, the biggest leading force for district heating network to decarbonize will be the efficient district heating and cooling definition, which was established in the Energy Efficiency Directive. And you can see that we have milestones starting from 2028, and member states can choose from different options what they would like to meet to achieve the efficient district heating and cooling criteria. And you can see that in the green option, the renewable energy and waste heat is treated equally. So that's very positive news. Waste heat and renewables can jointly come together to decarbonize the district heating network. And by 2050, all networks have to run completely on renewable and waste heat sources. The Energy Efficiency Directive also introduced a new measure, the local heating and cooling plans, which will be mandatory to be developed by municipalities which has at least 45,000 citizens. This mapping will map the potential for increasing energy efficiency, also considering low temperature district heating networks, high efficiency cogeneration, waste heat recovery, and renewables, and it has to respect the energy efficiency first principle, the Planning Act. And it says that from mid-2026, every municipality above 100,000 citizens have to create a heat planning, and by mid-2028, every municipality above 10,000 citizens have to create a local heating and cooling planning, which is amazing. That means that in 4 years in Germany, there will be 11,000 municipalities having a map like this. Here on the left, it's a picture from Hanover. And you can see this is the draft, what they published a month ago. And you can see that currently they run mainly on individual natural gas boilers. They have 27% district heating network, but the rest is oil and other local heating solutions like biomass. But based on the local heating and cooling plan, what they just drafted, they plan to have by 2045, 56% district heating network, 34% heat pumps, and then 9% other local heating systems, which means that Hanover has more than 500,000 citizens. That would mean that the local district heating network would be larger than 250,000 consumers, which is huge. In this case, Hanover had to look into where is what heat source, what they can use and what they can deliver to the households, and where is the biggest demand, and what is the best energy efficient solution for them to be heated. Then the EED also introduces a new measure for data centers, which mandates every data center above 1 megawatt to use their waste heat. And this should be transposed by late 2025. But of course, there are exceptions. If the data center is technically or economically not good to be connected to a district heating network, then it doesn't have to. For example, if the quality of the heat is not good enough, they don't produce a good quantity of heat, and economically it doesn't pay off to build all the infrastructure to connect them, then it's an option to opt out. But we hope it will be not the case. And a month ago, the Commission also published a new delegated act, which will require data centers to report on their sustainability. So data centers will have to report to their member states on waste heat reused, if it's reused, the average waste heat temperature, and also of the types of refrigerants. So if it's air heated, water heated, and also how it is cooled. Sorry, if it's air cooled, water cooled, and what is the gases they use, and or if it's district cooling, which is also an option. Then the EED also introduces new assessments, which will require that thermal electricity generation installations, industrial installations, service facilities like wastewater treatment plants and LNG facilities, and data centers will have to look into the possibility to provide waste heat. Yes. I will speed up a bit. Also in EPPD, that's the Energy Performance of Buildings Directive, which was finalized few months ago, but in the council it will be voted only tomorrow. So it's just freshly finished. We see that they created a new zero-emission building definition, which allows all efficient district heating and cooling systems to be connected. So after 2030, all new buildings have to be zero-emission buildings, and renewable and waste heat can be connected to them, and also all district heating networks meeting the efficient district heating definition what I presented before. So that's amazing news. Here we can see that waste heat, renewables, and also district heating cooling networks in the process of decarbonization can connect. The Energy Performance of Buildings Directive also introduced new measures against individual fossil fuel boilers. For example, they phase out subsidies for fossil fuel boilers from 2025. These incentives for their installations. And they also introduce a phase-out date for fossil fuel in heating and cooling with a view to complete phase-out of fossil fuel boilers by 2040. That means that member states can decide on earlier date, but by 2040 it should be phased out. Then if we turn to the Renewable Energy Directive, we can see a lot of changes regarding waste heat as well. For example, the sectoral targets which were introduced for heating and cooling, district heating, buildings, industry, they can all count with waste heat as well. So for example, for heating and cooling, we have an annual binding target of 0.8% increase until 2025 and 1.1% after 2026 until 2030. And from this percentage, 1.1% up to 0.4 percentage points can come from waste heat. If a member state decides to count waste heat towards the renewable energy target, then the renewable target increases a bit. So by half of the amount what the waste heat provides. So for example, if the waste heat comes like 0.4% is waste heat, then the whole target increases by 0.2% points. And this is the case for the other targets as well. And in red, we see also different measures how waste heat is recognized. For example, district heating systems, large district heating systems, which use more than 25 megawatt are encouraged to connect to third-party suppliers, which could be renewable and waste heat. So, for example, if there is a waste heat source and there is a district heating network, then the district heating network is encouraged to use that. And also, where it is necessary, member states can put in place coordination frameworks between district heating operators and waste heat providers to communicate and to ensure dialogue. And also to achieve the heating and cooling target, member states will be endowed to implement at least 2 of 12 measures, and one of them is to implement risk mitigation framework to reduce costs for the development of renewable and waste heat projects. So that's an option, but it's only one of the 12, and member states have to choose 2. So let's hope the member states will opt that option. And we also see other legislations picking up on waste heat. and how they could use it. For example, the Urban Wastewater Treatment Directive, which was also not long time ago finalized, introduces that all wastewater treatment plants have to reach energy neutrality by end of 2045, which means that they have to produce the same amount of renewable energy as they consume. And they can produce, for example, biogases, but also, luckily, they introduced that the recovery of waste heat, either on-site or off-site with district heating network, can be counted towards this target. So that's very good news. And urban wastewater treatment plants will have to develop energy audit. That they have to undergo energy audit, and this energy audit have to measure how much heat they could produce and provide. And if we are looking at the money, which is also very important for development of new projects, we see that the EU taxonomy encompasses the utilization of waste heat. So if they are going to be used in district heating and cooling networks, it applies for the construction and the operation of the facilities that generate heat and cooling through waste heat. So that's very positive. And also we see that in state aid, district heating networks using waste heat will receive money to connect waste heat sources and to meet efficient district heating and cooling definition, so to connect more renewables and waste heat. So it's all there, and district heating networks will receive money for waste heat use. And that's everything from my side, and I am happy to answer your questions at the Q&A section.
Thank you. Thank you very much, Andras, for your presentation, for this relevant overview on the policy aspect of waste heat recovery. I'm pretty sure you have already some question in the chat. It's up to you if you want to already answer in the chat to this question or wait for the question in the A section. Thank you again. Now it's time to change a little bit perspective and going more into the technical aspect of district heating and cooling solution with our next speaker, Kam Bisul. In this case, I want to thank you not only Kam Bisul that is with us this morning, but also Christian Keim that participate in the writing of the presentation, but could not attend the webinar for last minute working commitment. But Com is with him and will present the La Seine-sur-Mer demo case of rewarded project. Com has a master degree from Supelec and a Master of Science of Applied Mathematics from the University of Heriot-Watt in Scotland, and another Master of Science in Mathematical Modeling from the University Pierre and Marie Curie. Com is a research engineer currently at EDF and is working on optimal planning and load forecasting for heat and power plant, decentralized energy system, or hydroelectric valleys, as well as on the planning of load shedding. Without further ado, please, Com, you can take control of the presentation. The floor is yours.
Okay, thank you for the introduction and for the invitation. So we are going to talk about La Seine-sur-Mer. First of all, a small presentation about the network. So the initial network was quite small and was extended for the rewarded projects. You can see here that there's a casino, a few residents, and other buildings were connected afterwards, mainly schools and also housings. So what's happening in La Seine-sur-Mer is that we have a connection here with the sea. so the sea is able to give calories to the network, but also to take calories from the low temperature network as well, depending on the season and the external temperatures. So we have different buildings. All of them have local heat pumps to have higher temperature for in the water, but they can also have chillers depending on on what they need during the year. What's also interesting is that the casino is needing quite a lot of cold because of the slot machines that are producing heat during all day long, basically. So the casino can give back some calories to the network, even in winter or in days like today where it's not that warm, but so some buildings may need some hot water, but the casino can produce some calories for them. So there's an exchange between all the consumers. Okay, so here are a few pictures. So we have the pumping station here, just behind it. So on one side there's the sea, on the other side there's the casino. Nice heat pumps and pumping the exchanger with the sea. Sorry. Here are some of the buildings that are that consume some of the heat that's produced. Okay. The next. So there were quite a number of modifications. So first of all, the network, as I've said before, was extended, but also there was some installation of variable speed pumps in the low temperature loop. So it's to have a better control on the system and also to lower the electricity consumption. Also, there were some communication issues that were solved because I will show you a bit later on how we control all this, but we need to have information about all the substations at all times. So there's a need for 4G communication between all the substations that are in the city, basically, as I showed in the previous slides. Okay, so again, some few pictures of our last visit in the pumping station, different SCADA and automaton seawater filters, but that's just an illustration of everything else. So here is a scheme of the different substation with the heat pumps. As I've said before, some of the heat pumps are only needing heat, like this one. Some of them are also needing cold. The casino needs heat and cold, and also some of them need domestic hot water. A first picture was made of all of this to see how the coefficients of performance of the different heat pumps were, yes, if they were quite good or not that good. So here's so some of them have a quite a low COP, and some of them are already working quite efficiently. And that's something we're also dealing with on the optimization side for of the project. Some other improvements are in progress. Some heat pumps where one of them was a bit oversized, so it was working not in a very efficient way, so it's being replaced. We're trying to reduce gas backup, in one of the substations by changing the heat pump with a high temperature one. We're also working in or at least Dalkia, because most of the work is done in collaboration with Dalkia. Is working on adding a new heat exchanger in the casino. Yeah, and we'll be talking for the end of the presentation about our tool called Demix. Demix is a tool that we're developing together with Dalkia to have to control heat networks. It's it's separated in two parts. One part is the mix conception, which deals with how to design a new network. And the other part is about real-time management. So first of all, how to forecast the demands, cold and hot demands. And the second part is how to optimize the operation. So we'll be talking mainly about this part, the one that I'm very familiar with. So load forecasts. So we've developed a tool that is called Forecast Heat. It's based on machine learning algorithm, mainly generalized additive models and random forests. What it does is you basically take 1 year or more of past data, past consumption. You combine that with meteorological data, and then you have a model that's able to forecast the consumption for the next few days. And when you use it in an operational way, you just give it the weather forecast, of course, but also past consumption, last day, for example, and past outdoor temperature, and you can have your load forecasting for the next few days. There was one difficulty, interesting difficulty, of course, here in La Seine-sur-Mer with the casino. So casino is consuming a lot of cold during the day. This because of the slot machine, like I've said before. The cold depends highly on the occupancy rates because slot machine only work if some people are playing with them. And so we had work to do to see if our tool was capable of forecasting the cold correctly or not, especially since the occupancy rate can be tricky data to have. The casino send us a few past data to check if we could have something interesting with it. What we saw is that our tool is already capable of forecasting quite well this occupancy, and so it's capable of integrating that in its cold load forecasting. Why? Is just because basically people are predictable in their going when they go to the casino. Basically, they go on Fridays, Saturdays, during the holiday breaks. Like you can see here in on the 31st of December, people are quite happy to go to the casinos. So that's 2 spikes here. And so we're capable of predicting that quite well. So our tool was, we didn't have to make some improvements to our tool, which was already efficient. We tested also other variables to forecast cold, but we didn't have sufficient and significant improvements. So it was, we kept our usual data, the same one for heating and cooling. Okay, so we had some troubles in La Seine-sur-Mer due to different things. First of all, we had COVID, which our tool is based on past data. So with COVID, especially in the casinos, the demands were modified for quite a few years. So it was a difficulty we had to deal with. Some new substation, we have to wait a bit for data to arrive or do something else for the forecast. We also had a few questions. We worked a bit, sorry, in to correct the weather. The point here is that the weather station is based in Toulon, which is quite the Météo France weather station where the forecasts are made is based in Toulon, a few kilometers away. You have to cross the sea. It's in the airport, so the weather can be a bit different. But we showed that this was not such a big deal, and we didn't have any correction to make, which is quite a good thing, especially since we want to be able to deploy our tool, forecast it in very different places in France for Dalkia. So everything is perfect here. Then on the optimization part, what we usually did before was, thanks to forecasting the demands, we do an optimization, we get a planning. So we have different values coming in, prices, productions, waste heat production, etc., etc. We optimize everything, and then we get an hourly. We get what the loads of the different machines on an hourly time frame for the next few days. That's what we usually do. What we've tried here, but without so much success, is to have a better physical representation of the system, thanks to a connection with a model, a physical model, having the optimization talk with this model and to have to be able to have a better representation. It was not such a success, and it was the complexity here is to have one optimization model and one physical model, which is not very easy to implement in all the different cases we can have with Dalkia. What we've done also is to you work with mixed integer linear programs. There are a lot of interesting characteristics, and we work a lot with this kind of optimization techniques, but it's not enough to model the nonlinear parts. So you all know that there's a lot of nonlinear equation in heat pumps, for example. So we're working more with mixed integer nonlinear programming, and our tool is new tool is based on this this framework. So it's very interesting for us, and so it's easier to model physics with that. Okay, so I'll go a bit faster, but our plan is to have DMX on top of the Dalkia informational system, working with on a more local level, getting information. What we're doing here in this demo site is we have a DMX in a Amazon Web Service server. We have local automaton, and we have just a dialogue between them through the internet. We're getting data, we're sending orders for the different machines for the moment. Yeah, one of the problems with 4G communication here, which can be difficult considering where the automaton are located. But okay, so far we've already started the tests, and it's working quite well. Is a screenshot of what we're doing to compare what's on site and what our optimization software is saying. Yes, and for the moment we've been identifying where to work, what kind of things we can control, and we are currently giving a few temperatures orders for the low temperature heat pumps. We're still working on the most desirable control strategy. What do we want? Do we want to minimize the total consumption, the total bill, and at the same time we have to take into account the heat pump's efficiency and minimize also the consumption of the pumps for the loop. So there's a lot of things to be done here. Merci pour votre attention, as we say in French, and I'm happy to answer any questions you may have.
Thank you. Thank you very much, Com, for your presentation. In this case, I need to ask all the participants if they have some question to write it in the chat, and Com will answer to you later on in these days, because now I know that he needs to leave. But I really want to thank you for your participation at this webinar, as well for the presentation, even if it was just a last minute invite. So thank you again. And now we can go on with our third speaker of the day, Hugh Moore, that is going to present innovative case from the Glide Gateway Energy Project. Hugh is a project manager working at Glide Gateway in Glasgow, and the largest remaining urban regeneration company in Scotland. He has been involved in developing the organization energy strategy and delivering the company energy projects, with over 30 years in project management and currently a postgraduate at Glasgow Caledonia University, specializing in renewable energy and environmental management. I don't want to steal you more time because I'm pretty sure your presentation will arise several questions. So please, Hugh, it's your turn to take control of the presentation and start. Thank you.
Okay, good morning, everyone. Thank you for inviting me to this event. I'll tell you a wee bit about our journey in Scotland to renewable energy and a wee bit about Clyde Gateway itself. So Clyde Gateway is the largest urban regeneration company in Glasgow. The red zone here shows you where that is, also the home of another famous Scottish football club, for those that are familiar. But our focus is particularly with a community focus, and I'll touch on some of the policy and particular pricing strategies that link to the technical solutions that we've employed within Clyde Gateway. Our area is shown here and outlined in blue. So we straddle both sides of the River Clyde in Glasgow, and covering both Glasgow and South Lanarkshire. So just in terms of some of the background, our story goes back to our Energy and Carbon Master Plan that was completed back in 2012. But the landscape in Scotland has changed quite significantly over the past few years. But although we were the first area to be identified as a green regeneration innovation district in Scotland, but most recently, the work with government has been focused on the development of heat network legislation and heat and building strategy, and specific plans locally for local heat and energy efficiency strategies. These are the policy documents which all local authorities in Scotland have had to complete by the end of last year. And these look at particular zoning proposals for district heating and cooling networks within the Scottish context. Our particular steps towards integrated energy looked at a number of areas. Our first intervention was in relation to our community energy project. The focus for this was largely around developing relationships with key stakeholders, particularly Scottish Water, who are our national water company. But secondly, our interventions around district heating and cooling were focused around accessing the sewage network as part of Scottish Water's infrastructure. And one of the third areas that we've looked at is through the British Geological Survey, with a particular focus on waste heat generated through shallow geothermal mine workings. Those elements have all developed towards us delivering our D2 Grids project, which is a European funded Interreg project, which I'll talk about a wee bit further down the presentation. So our areas here, the light blue area that I'm showing is the Dalmarnock Wastewater Treatment Works, which is owned by Scottish Water. This is an asset which is very close to our main master plan sites, which are shown in green in Dalmarnock and purple for Shawfield. And that proximity of the wastewater treatment works has been a very critical factor to how we have developed our whole strategy. Our first sort of intervention was to install pipes in the ground to make sure that we were starting to deliver a network. And the first project that we delivered with Scottish Water Horizons was a CHP-based scheme, a gas-based scheme. But the primary reason for that was in relation to making sure that we could get infrastructure in the ground, as part of the kind of key issue in terms of integrating with end user customers was that we weren't able to make the decisions about investment for heat networks without that demand certainty. So we had to make that decision, and we've funded projects on a revenue deficit basis in order to ensure that that infrastructure is in place. And whilst that is a CHP-based scheme, it's one of the kind of key challenges for us at the moment, which links to the D2 Grids project, where we're looking at how we can transition from CHP. Probably the most common solution in Scotland at the moment is CHP, but in terms of transitioning away from that, one of the key considerations, because they have largely been a product of electrical generation, is how to solve that particular question as part of that transition arrangement. And as it's been touched on earlier, the local heat and energy efficiency strategies are a key focus for us. This is a win for Glasgow, where we've identified some of the key zones within the area that would be suitable for heat networks, and within that identified our area as a primary zone with secondary potential to look at integration of that sort of system. And I suppose for us, part of the key process, apologies, that slide has jumped across, has been looking at integration. It's became a particular key issue for us because of the traditional schemes that we have, as I say, based in CHP, but where we've looked to integrate more with other networks that are existing in our area, and how lower temperature systems can integrate with that. So within the energy centre that houses the CHP, we've already installed additional heat pump technology, which is using the treated effluent as waste energy as a potential preheat for CHP as part of a sort of transitioning arrangement, as we look at the potential for full transitioning. And clearly we're moving in terms of that journey very quickly. So we don't have the pedigree that most of Europe has in terms of the learning of third and fourth generation schemes, but we're actually moving much more quickly within a very short period of time from those schemes to much lower temperature solutions. One of the key challenges that we have in relation to that is obviously the electrical pricing for the use of renewable energy technology, heat pumps, etc. And our electrical infrastructure is part of that issue as we move from today's network to the future, where it's much more integrated, and trying to deal with that key differential, which is the pricing mechanism, which I know varies throughout Europe, but in the UK in particular, the differential between electrical and gas pricing is very significant, which proves a challenge really for introducing renewable technology that is based on a sustainable business case. And we've sought to do that through a couple of schemes within Scotland. There's an AMID scheme in Renfrew and our own scheme in Clyde Gateway that looks to optimise the options for delivering that. So our D2 Grids project, based in the Interreg North West Europe programme, was led by Mijnwater BV in Holland, with a range of demonstrators from Bochum in Germany, Paris-Saclay in France, Brunsum in the Netherlands, and Plymouth in England, as well as ourselves, and looking at those lower temperature circuits through ambient loops, using heat pump technology, but in this case, us integrating with our Scottish Water Energy Centre, and using the infrastructure that we have to deliver the demonstrator project. Very much focused, obviously, on the net zero approach and the introduction, and largely because of the electrical constraint that we have in this locality, to develop solar and battery solutions that provided local generation of the electrical requirement for those systems. So the wastewater system that we use provides substantial flows, substantial output that can contribute to our district heating and cooling. We are only delivering at the moment around 2 megawatt of heating and cooling for the initial connections, but the potential is there obviously to grow that further. And although the main focus for us has been because of the proximity of the wastewater treatment works, we've identified that accessing the sewage networks itself for wastewater has proved problematic, particularly from the capital expenditure side in terms of the infrastructure that needs to be in place for those to be developed, has generally proved to be fairly unviable in terms of a long-term business case. So maximising the proximity of wastewater treatment works to development areas has become a key strand of policy activity too. And that type of system is obviously benefiting from a much more use of smart tech, which has been touched on earlier in the presentations, in terms of managing those closed loop systems, optimizing efficiencies, and how we manage the different energy flows as part of that, on the demand side in particular. There's been some key challenges around that in terms of load information, optimizing the decentralization use, and greater efficiencies that can be developed as part of that. But in large part, we've focused on the wastewater systems as a primary means to deliver long-term potential for district heating and cooling objectives within our area. And the systems themselves are generally fairly straightforward. We are obviously utilising that resource that's already been through its completed process. The wastewater treatment works is delivering all of the sewage effectively from the east end of Glasgow through this wastewater system. And we are effectively just tapping into the effluent around 12 to 15 degrees or so as the energy source for our ambient loop. So deliverables, we are extracting from that effluent through our heat exchanger, integrating our heat pumps as well as part of that process, as well as introducing the solar array elements and battery storage with a separate decentralized energy substation, which is then delivering that heating and cooling to the end users. So our key activities, which are perhaps proving more challenging really than the technical solution, is developing our outline business case in a sort of holistic way, and a range of technical governance and financial modelling that had to support that case. So our investment was very much based on the ability to prove a revenue case that would support that. And in some instances, that still proves a bit challenging, as I mentioned earlier about the pricing differential, but there are also more structural issues in relation to pricing mechanisms in terms of pass-through costs from our local electrical supplier that can have an impact in designing large-scale schemes. And that's a policy challenge, which is still part of a conversation that's been had between government authorities and ourselves. But in terms of delivering the scheme, we used our Smart Bridge, which also is another EU-funded project, connecting communities and delivering pipe work and infrastructure to the relevant locations. And this is a schematic of what we've actually delivered from the extraction point at the wastewater treatment works, our pipe work infrastructure, point 4 being our energy substation, where we've effectively got the decentralised heat pumps, chillers and electric boilers, and a ground-based solar array, which is effectively providing that local generation to manage the energy substation, but also providing some elements of local private wire solutions, which forms another sort of key component to the business case side of overall viability for this type of low-grade waste project. And in the longer term, as we develop that schematic out, the ambient loop is extended to develop those and allow energy flows to be managed between the different solutions that and end users. So one of the key components for us is trying to drive the demand side in terms of further diversification. So where we're combining commercial buildings with residential buildings in particular, to optimise the energy efficiencies within that type of scheme. And in terms of that D2 grids project, these were the kind of key components that we focused on in terms of the principles that needed to be delivered, looking at closed loop energy systems, optimising low-grade energy sources, and the decentralisation of that demand-driven supply, and also developing an integrated approach with local energy sources. And these very much reflect the principles that the D2 Grids project is looking to secure, essentially trying to generate as passive a solution as possible. And in terms of the KPIs that we'd identified, we were looking at how we could perform better in respect of that demonstrator. We performed well in a number of areas in relation to local generation, but as you can see here, the key areas in terms of those principles that need to be developed are largely around customer connections. So the demand-driven side, which needs to be optimised to improve that efficiency, as well as improving the local energy supply through the electrical requirement. Those are the two kind of key fundamental constraints that help to optimise that system. And we're looking at a range of modular growth that will start to fill those gaps as we develop that. So in terms of what's been delivered is an integrated sort of solar-based solution with battery storage, which we're looking to expand. It happened as a result of a revised plan. It wasn't intended to do it this way, but the business case seemed to call out for a larger scale element of local generation, which in this case was solar array, to help support that, and it became now an integral part of that business solution. And these are some of the levels of generation that we're doing as part of the demonstrator project for the initial phase. And we're connecting our existing buildings. This is a red 3 magenta, where we've completed the retrofit of the plant room to bypass the gas boilers, and we will build out effectively the rest of this site, which is our magenta business park for commercial use. But key to that is the level of diversification that can be provided as part of that. And in relation to that, the site next door to our magenta business park, which is a former football stadium, is now proposed for around 400 residential units. And part of that next stage business case is to integrate that with this system, which in terms of the outputs that we've estimated as those connect, provides for the greater efficiency of that overall waste management system, in terms of which energy is being delivered to that site. And then in terms of next stages, we're looking currently at our other kind of key science-based project, which is located in our area. It's called the UK Geoenergy Observatories project, but it's run by the British Geological Survey, which is a science-based project over a 15-year period, which is looking at the scope for optimising the use of geothermal energy. The boreholes are all located within our Kuniga Park area, and the information that is that's coming out of that is essentially suggesting that we have the scope to integrate this solution with other renewable sources, such as the waste energy scheme, to look at also that being a part of transitioning from the CHPs, which are quite prominent in the area, to find longer term solutions for that. And there's a range of experimental equipment that's available there to academics and other business users to test various solutions that would help integrate that. And these just a range of the borehole facilities that are in the area at the moment to support that type of scheme. But very much as Scotland, I suppose, but us in particular, are looking at next stage lower temperature schemes such as D2 grids. We're already looking at how all of those elements can form part of a wider integrated plan to allow us to be able to achieve decarbonisation substantively by 2030, and obviously ultimately by 2045 as part of those targets that have been set by the Scottish Government. And we see that as a particular focus of work that needs to be looked at in greater detail as part of those renewable energy sources, where they are mixing effectively or integrating with different types of schemes towards the solution to those areas. And you know, some of those elements are around the risks that are associated with delivering these projects. And our particular issue has always been around the business case, as much as obviously the technical solutions are there to be developed. They need to feed into revenue models, and this becomes a particular issue for us in terms of pricing mechanisms for end user customers, particularly local people, in an area which have got relatively high levels of deprivation. So all of these form part of that probably more complex area of work that needs to be undertaken. And in terms of making it work, our approach has largely been focused on taking a staged approach, but running our business models alongside those areas to optimise the scope that increased use of renewable energy sources can provide towards our decarbonisation plans. And I think that is me, and I can hand back to yourself, Julia.
Yeah, thank you. Thank you very much, Hugh, for this wide presentation, not only on the project Grid to Grids, but on all the several projects and solutions you are working on and you manage in this period. And I'm going through the rest of the agenda with our fourth speaker of the day. We have a really full agenda, so we don't have time to lose. I want to introduce you John Sommer is our next speaker. It is a scientific lead in data center and research at the Research Institute of Sweden, and adjunct professor in fluid mechanics at Luleå Technical University, and visiting professor in thermofluid at the University of Leeds in UK. John has worked on government and the studentry funded project, making use of computation, and chaired the high performance computing user group for 20 years at the University of Leeds. For more than a decade, John's research has focused on many thermal and energy management projects within data center, including liquid-cooled IT research and multiple scale, and further transformed by opportunity of integrated digital infrastructure research at the RISE ICE test and demo data center facility, which includes large test beds supporting thermal energy recovery. His research at RISE during this decade is focused on making the digital infrastructure more energy and resource efficient. And today is going to present us the demo case of the project WE District. And thank you, John, for joining us. I leave you the floor.
Thank you very much for the introduction, Julia. Thanks for the invite to this meeting. So yes, if I get going here. We are going to talk about this WE District project. It's a Luleå demonstrator, and I probably need to tell you where Luleå is located. So a little bit about the ICE data center. So we're located up in the north of Sweden, just a few clicks south of the Arctic Circle. We're located up there because there is a data center cluster, and our research is around data center at the ICE data center. It's all about data centers, and we have quite a few partners working with us on this. So Ericsson and ABB, Vattenfall, Meta have been founding partners, and the local university, as well as some more wide-scale industrial partners like Vertiv and Castrol and Intel. And so, our research has got us quite famous in this domain because I think we're quite unique in what we do, dedicating our effort to data centers alone. And of course, we have a very friendly neighbor data center, which is pulling 120 megawatts off the grid today, which is the Meta data center next door to us. So We District was a project that we got involved with to look at smart and local renewable energy sources for district heating and cooling. This is the title, Solutions for Sustainable Living. And the idea of this project was to use a lot of different solutions and technologies to support district heating and cooling. And of course, I'm not going to go into the whole details of all the projects, all the demonstrators and all the technologies within the project, but there are multiple sources of renewable energy. We need to move to more fossil-free sources of energy for heating, as well as for electrical production as well. And of course, we need to use some solutions like advanced thermal storage. And today, we use a lot of IT systems to monitor and control all of these systems. And now data centers in the loop is a really interesting one. And I know Andres mentioned about data centers and the excess heat, and I'm going to talk a little bit more about that. So the particular demonstrator that I'm going to talk about today is actually based on this idea of recovering heat from the data center, but with a slight twist. So let me go on to talk about that. So why do we talk so much about waste heat from data centers? So the main issue we have, and this goes back to some very interesting research done in the 60s. Rolf Launder was a researcher at IBM, and he was always cross with his colleagues because everybody thought that using digital systems didn't actually consume any resource or energy. And so he's trying to make the point clear that it's actually physical, and this is very true. Today we're seeing the absolutely massive explosion in data center build out. I mean, in 2023, I think the US alone has put nearly 3 gigawatts of data centers on the map. So all the electricity that goes into a data center, 99.97% of it is converted to heat, and that's because the processes that do the computation, that do the processing of the binary digits, that supports the digital infrastructure and supports those applications that we all use, only a small amount of that energy is really needed to actually do the processing. So there's a strong motivation, particularly from the EU, as was pointed out in the first presentation, to try and recover some of that heat. And a lot of the installations today are using heat pumps, of course, because we need to upgrade the heat from a low grade of temperature. So if we look at the EU in terms of derived heat production, I got this data from a number of different sources, Our World in Data and the Eurostats. So derived heat production in 2019, for example, was 622 terawatt hours. And in that time, the EU population has risen by 4% since 2000. Waste heat only accounts for 69 terawatt hours, so that's 11%. And if you look at this pie chart here, you can see that some of the waste heat is from non-renewable sources, non-renewable waste sources, and some of it is from renewable waste sources. Question is if you recover heat from data centers, is that non-renewable or renewable? And it depends obviously on the electricity consumption of the data center. So if you are running your data center on coal or gas-fired energy systems, then then that is not a non-renewable source of electricity, but recovering the heat is still a valuable process, thing to do. So if you look at the data centers in Europe, I mean, the figures are a little bit all over the place, but I think some statistics put it around about 80 terawatt hours of energy, electrical energy consumption per year. So if we could recover a good 90% of that as in terms of heat, then that is quite a significant chunk of the derived heat production in Europe. So this is the motivation for looking at data centers as a source of heat recovery. The big problem we have with district heating is usually used in households, but of course in other buildings as well. But if you look at the breakdown of how energy is consumed in households, 64% of it is in space heating, 15% of it around is in water heating. The problem we have with data centers, as the first speaker said, operate continuously all year round, and they're generating heat all year round. But the heat demand from the consumers obviously fluctuates. And here is actually this was actually taken from the heat roadmap. This was looking at an average. I don't remember which year this was, but it's a recent year, looking at the heat, the daily heat distribution. I think it was normalized, so that's why 100%, it goes from 100% to 0%. But during the summer months, you can see, during the warm months, we don't need space heating. We need hot water, but we don't need space heating. So the demand drops dramatically. And so this is a challenge for data centers to try and deal with this, because they'll have to use other mechanisms for rejecting the heat. And of course, you want to reject the heat somewhere else, and usually in the summer, it's actually more difficult to get rid of the heat from data centers. So not only does nobody want the heat, it's actually more difficult to get rid of the heat. So if you look at some of the where it's being done today, I've listed some here. Yandex, Facebook in Odense, Denmark, Yandex in Finland. There's the Swedish Energy near Stockholm. There is Val d'Europe in France. There's others. There's quite a lot of waste heat recovery from data centers. It's not a new idea, so it has been developed over quite a few years. And one of the things about all of these projects that I've just listed here is that it involves the energy provider. So the energy provider is obviously the district heat supplier, because the question about data centers is who owns the heat pump. So this was taken from Facebook's sustainability report. And here they're talking about, rejecting the heat from their data center here, and feeding it to, obviously getting it into water, or transferring it from air to liquid, and then transporting it under the ground to the district heating substation, where the district heating substation owns the heat pumps and then upgrades it for distribution around the network. And of course, in Sweden, where I'm located, the district heating networks are very high temperature. So they are actually, in Luleå, for example, the temperature in winter is nearly it's over 110 degrees centigrade. In summer, it's around 72 degrees centigrade, which is quite challenging for data centers when you've got hot air coming from a data center that is only between 25 and 35 degrees centigrade, and you've got all the losses in trying to capture that heat into liquid form. So heat pumps are in the loop, but the biggest issue, and this could be a point that we can discuss in the Q&A session, is about who owns the heat pump, because I've got lots of examples of where data centers own the heat pump and some issues with that. Perhaps one of the most recent projects, and I was attending a talk at LUMI. LUMI is the largest high-performance computing data center in Europe, based in Finland. And here, this was a picture of a slide that I took just it was about 6 or 7 months ago. You can see that they got about 9 megawatts of computational load. they can either reject it straight through heat exchangers to dry coolers outside and reject the heat outside. And they can do that at low overhead because they're not using any compressors, or they can push it through the heat pump and then distribute it to the district heating. The interesting thing, maybe you can't see it so easily here, is that the supply temperature to the IT is 32 degrees centigrade because it's liquid cooled. Here's a picture of the liquid cooled technology that they're using, and it's 44 degrees back from the IT. So to get it up to the 88 or the 90 degrees that they need for the district heating, they have to use a series of heat pumps in the loop. And so they own the heat pumps, but it also has an effect on their overhead for running the compute, because that is the compressors are quite energy intensive. So what did we do in the WE district here then in this project? So we were tasked to build a small edge-style data center. So we were going to demonstrate liquid-cooled edge, and it had to be quiet. So we didn't want any, lots of fans or loud compressors, etc. And we wanted it to have a low impact on the electrical grid. So we also we needed to provide on-site electrical production, and also to provide heat for the adjacent building. So the concept that we built in Sweden was based on 3 containers. We have a storage of locally produced biogas, because we're going to run the whole system on biogas. And it's of a grade that is used in the automotive sector. So it's not raw gas, it's being processed to be, it's essentially biomethane, 97%. And then we wanted to use fuel cells, and we use the high temperature fuel cells, the solid oxide fuel cells in the loop, because they are able to produce the electricity, but they also generate quite a lot of heat. And then we also had a container that housed the data center, and the data center was essentially, we repurposed some open compute project servers that were donated to us by our friendly neighbor. And they were air-cooled, but we repurposed them for immersion cooling, which is actually sinking them into a tank of dielectric coolant and operating them fully submerged. The challenge is the climate in Luleå, and I will explain a little bit about that in a minute, because the swing of temperatures is quite large. So this is a picture of what we built. So you can see this is the main facility here, which is going to be the heat demand. On the top here, you have the container with the fuel cells. There were 9 solid oxide fuel cells that were put together. In the bottom container, we had the data center, which has got the immersion tank in it. And around about 13 or 14 meters away, for regulation purposes, we've got 2 tons of biogas stored at 150 bar. Not all, obviously, we're consuming it, so the pressure drops as we consume the gas. But there's a pipeline to the fuel cells in the ground here. And this is the main demonstrator from RISE for the WE District project. We ran this project for a while, and we've got some data that we can share with you. But just to talk a little bit more about the concept. So the fuel cells, in order to operate, require 3 things. They require a lot of air, they require biogas, and they require water. So we're supplying, they're connected to the water supply of the building, because they need the water to do the steam reforming process to get the hydrogen for the electrochemistry of the fuel cells. And they also, the incoming air, the idea here was to actually preheat the air. And this concept was put together with our partners at IREC in the Research Institute for Energy in Catalonia. And is to use the heat from the data center, which is actually not, when it's immersed, it's slightly hotter than you can get from air, but it's still low temperature. But the idea was to take the outside air temperature and preheat it into the fuel cell container. And the fuel cells then would ingest this warmer air and on the back of the fuel cells just before they exhaust from the fuel cells, because they do exhaust some carbon dioxide, some water vapor. We needed to collect the heat. We needed to harvest the heat from the exhaust, and that's what was used to connect to, not directly to the district heating, but it's connected to the building loop, which is the secondary loop. So the idea here is that we can't match the temperatures of the district heating, which is at 110 degrees in the winter, but we can relieve the energy requirements from the building, from the district heating network, by supplying to the actual building. You can see the connection point between the containers here and the building here. We also had to insulate it. We also had to run a little hot wire through it, so it's additional power, parasitic power, that we have to make sure that nothing freezes with the outside temperatures when they drop below -20, which is quite challenging to operate. So here are some pictures of what you can see inside the data center here. So this is actually the immersion tank. So we've got around about 22 kilowatts of IT here. So it's a small amount of IT power, but it's designed to present the concept of an edge style data center. So one that you would put in an urban area that wouldn't be noisy, that wouldn't impact on the electrical grid, but could be connected to the gas grid if you were pumping, say, renewable source of natural gas, biomethane, for example. The servers were running on a DC bus in the tank, so we only had to provide power to 2 power shelves. The power shelves were 3-phase, and what we did is we connected the 9 solid oxide fuel cells, because they were single-phase solid oxide fuel cells. We connected them in sets of 3 onto each of the 3 phases. They were connected to the electrical grid. So the way that it worked was that it wasn't directly feeding the data center. It was the nearest point of electrical generation, and by Kirchhoff's law, the data center was consuming that electricity. But the issue with it is, and I'll show some data in a minute, is that the fuel cells have, being a high temperature of operation, they have quite a lot of inertia. So when I say, what I mean by that is, when you ask them to change their power generation, they take some time to change that power generation. You can see some of the temperatures of the heat recovery we managed to get from the system. It's in between 60 and 70 degrees. Nominally 65 degrees was achievable, depending on a number of conditions. And you can see that this is from the external temperatures. The weather, the outside temperature was dropping down to -20 here sometimes, but we were fluctuating up to 0 degrees sometimes. This is over a period of a couple of days from, let's see, this is in March, 6th of March, all the way to the 11th of March, 2023, this data was collected. So talking about the fuel cell production, so what I have here is actually a trace. The red curve is a trace of what the data center is demanding. So it's the electrical requirements of the data center. So these are the 22 kilowatts of, they're not operating at full power. They're operating at around 10 kilowatts here, but you can see the workload is fluctuating. And as the workload fluctuates, the fuel cells have to keep up. So here you can see one where the power is immediately gone from around about the requirements of power because of the workload on the data center has gone from around about 8.5 kilowatts up to 11 kilowatts. And the slightly purple line is trying to catch up. So this is actually the production and what is actually being produced by the fuel cells. And sometimes, when the power draw actually drops down, you can't see it so much here because it's a little bit too fine to close. But the fuel cells are overproducing. So when we're ramping up the power demand, the fuel cells are underproducing, and when we're dropping down the power demand, the fuel cells are overproducing. So in that sense, we really needed some kind of buffer of electrical storage, but at this particular installation was connected to the grid, so it was grid parallel, and therefore being grid parallel, it would if it overproduces, it pushes the electricity up the grid. If it underproduces, it draws from the grid. And so some of the results that we got in terms of the monitored energy consumption and from the 11th of January 23 to the 16th of June 23 was we consumed 72 megawatt hours of biogas, and the solid oxide fuel cells were able to produce 39.4 megawatt hours in that period of electrical generation. And so they are 54.6%. The whole system, the stack of 9 fuel cells, was 54.6% efficient in terms of generating electricity. The rest of the energy is heat and some other parasitic loads. In terms of the power meters, so of that 39.4 megawatts, there was some parasitic losses in the fuel cell container, lights, etc., a small pump, monitoring equipment. Only 38.5 megawatt hours managed to be extracted to enter the grid. And of course, the data center being the nearest point of consumption, that was consuming 48.65 megawatt hours. So what we're saying is that we managed to cover 79.2% of the electrical requirements of the data center using the fuel cells. In terms of the IT was only consuming 41.87% because we had a dry cooler, we had a small heat pump in here to maintain the temperature of the container, and there were a few other parasitic losses to do with the monitoring system as well. In terms of the heat, 1.4 megawatt hours was recovered of that 41 megawatt hours was recovered to preheat the incoming air to the fuel cell container. And from the fuel cell container, 7.8 megawatt hours was actually managed to enter the building as for space heating. And so we were recovering about 9.5% of the energy if you work out the gas as the prime source of energy. So it's the sum of these two, because we were pulling 0.84 megawatt hours off the grid for the fuel cell container, and we were putting 72 megawatt hours of gas into the container. So 7.8 megawatts of that was consumed. Megawatt hours was used as heat recovery. The fuel cell container has losses, which we calculated. If you do the energy balance, it's 28 megawatt hour. I mean, most of that has come out of the venting system from the fuel cell. So we were venting the air to outside. So the exhaust gas from the fuel cells was vented to the outside, and that was quite warm, but it was no longer hot enough to recover anymore. Although we operated for longer than half a year, this was the time when we actually managed to collect all data. And you can see there were dips here to minus 20. But the interesting thing is that with minus 20 outside, the whole system was able to produce 65 degrees centigrade hot water for the space heating in the building. Which, so the concept has some viability there. It's a small installation. If you were using a much larger installation, obviously you would have a lot more heat generation from that. So a few takeaways for you guys to think about here is the current setup of the demonstrator was capable of recovering 65 degrees of centigrade heat with minus 20 degrees outside. If we added further insulation, we could improve this because we had quite a lot of heat losses. The actual data center container, they were solid walls, they were concrete walls. And so inside when the temperature was minus 20 outside, inside the data center, the walls were very cold. So we were condensing some of the vapor in the room on the walls because of that. The fuel cells operated at 55% electrical efficiency, which is from locally produced biogas, which is actually quite a remarkable efficiency when you consider other systems. I mean, in terms of electrical generation, the only other system that can produce 55% electrical efficiency is a combined cycle gas turbine. And usually they're big and they're quite large systems, but this is a small system. And maybe the general discussion points here is, you know, a lot of people are talking about AI these days, and that's one of the reasons why data center power demand is growing quite dramatically across the globe. But AI workloads will be required for inferencing at the edge. So our interactions with AI systems need data centers close to us. Could we run this in island mode? Could we partially introduce green hydrogen into the solution? If we had electrolyzers and we have an overproduction of renewable energy, we could convert that into hydrogen and use that in the mix with the biogas. The noise levels were low, which is useful, good for urban deployment, and it also will reduce the load on the electrical grid. So with that, I'd like to thank you for your attention, and I'd like to thank all the partners that have been involved in We District Acciona for coordinating the project, and I'm available later for questions and answers if there are any. Thank you for listening.
Thank you, John. Thank you very much for your interesting presentation. I'm pretty sure that it's going to make arise several questions from our participants and maybe also from our other speakers. I actually can see that you already have some questions in the Q&A chat. So if you want to start answering them in the chat while we are going through our next and last presentation of the day with Jere Oksanen, that this time is going to present demo case from not a EU-funded project, but a national project. And Jere has been working in renewable geoenergy consulting and project for the past 5 years, and is currently working on innovative heating and cooling product, including utilizing decentralized waste heat production for district heating. Without further ado, I leave you the floor. Jere, thank you very much.
Thank you. I'll try to keep it a bit brief since I think we're running a bit behind schedule. But what we heard from so far is policy and background, which has been very similar to what we've got going on here at Helen. So that was quite interesting, as well as some technical aspects and heat utilization projects, and now very detailed one about data centers. But I'm here to bring you a bit of an overview from the perspective of an energy company. And first, I'd like to showcase this slogan of ours, they see energy in a new light, as an idea, so that maybe you can keep it in mind when you're thinking about waste heat and what kind of a value does it actually have. I see it actually the fonts have been changed now, so this might look a bit silly, but we'll just have to work with it. Helen, in brief, in addition to electricity, heating and cooling, we offer some solutions for regional renewable energy and electric transport. And we've set ambitious goals to be carbon neutral by 2030, as well as plan on to phase out combustion-based energy production by 2040. And Helen, in numbers, briefly, these are 2023 numbers. Carbon neutral energy production of already 55% and growing. And then what we're talking about mostly here is the heat production, 6.7 terawatt hours total. So we're talking about a major district heating producing company here. And the total length of the district heating network here in Helsinki is 1,400 kilometers. And last but not least, I would like to focus your attention on the electricity supply security, which is among the best in the world. And if you translate this number into something more every day, it results in one 30-minute partial blackout in 10 years. So quite a high level. Then some national context, as Helsinki and Finland might not be your expertise. Finland is one of the coldest countries in the world, and the heating of buildings is responsible for 27% of the total energy use, or about 74 terawatt hours. And the district heating is by far the largest segment in the country with a share of 45% or 34 terawatt hours. And that, to put that number into context, it's somewhere roughly the ballpark of France, but Finland has a population of 5.6 million. So per capita, it's one of the highest in the world, maybe only competing with Sweden and Denmark. Then moving on to Helsinki, it's the most northern city in the world with population over 500,000. The total population is 675, and the heating of buildings here is responsible for approximately 50% of the total end use of energy, and district heating is again by far the largest shareholder with 90% approximately. The rest going to transport and industry and living. And then at Helen, we have the largest energy consumption of any district heating network in the most densely populated city in this country, and all energy delivered will be carbon neutral by 2030, as I said. And waste heat is to achieve this goal, waste heat is a valuable asset in our climate goals. Moving on to achieve this phase out of fossil fuels and centralized production, we need to have a large district heating network and a solid electric grid behind it to serve as the backbone of a modern energy system that is flexible and capable of distributed production. And to do so, here I'm showcasing our network on our district heating network on the city of Helsinki. The blue areas are production facilities already that we have that are distributed. And to put the 1,400 kilometers into a context, it's about the distance from Brussels to Lviv in Ukraine in a straight line. Then the future of district heating and cooling networks here, as I said, the carbon neutral production by 2030 is the goal, and waste heat sources are an important part of this production portfolio. So far we are using purified wastewater, district cooling, commercial centers, the refrigeration industry, data centers, and also in the future electrolyzer waste heat from a hydrogen producing facility. Coal production will be phased out completely in 2025, and to do so, all of these distributed heat production facilities are required in the system, but this also increases the complexity of the system by a considerable amount, which means that the optimization of this entire system is not possible anymore with traditional methods, and we have a lot of digitalization here in the society to do with the optimization of production as well as demand side control. This is a significant opportunity, but requires a lot of investment and involvement, and hydrogen will play this role in the future to bridge the gap between the renewable productions and also the demand side of heat. And how to achieve all of that eventually, especially with the waste heat, it is together with our customers. So not only do our customers get value from selling waste heat to us, and also the cost savings from otherwise wasted heat and the electricity part, they also participate in the climate goals of our city in a meaningful way, creating sort of a brand value also. And what do I mean by all of that is that they're putting the waste heat into good use. We recover the heat from the companies and industry and use it to heat homes and properties throughout the energy system. Waste heat producing industry, data centers, for example, and the waste heat utilizing heat pumps, whether or not they are owned by the data centers or us, both enjoy, and their auxiliary equipment all enjoy low-cost electricity and a reduced industry tax rate for said electricity, as well as the very, very high supply security. For example, the Finnish electricity price in 2023 was 56 euros per megawatt hour. So here, because of the cold climate, population density, which create high demand for heat, and the economics of waste heat when it comes to electricity production and digitalization, both work together to match and help with our emissions reductions target. Then on to some customer cases. Actually, Telia's data center was mentioned in the previous presentation. So it located in Pitäjänmäki here in Helsinki and is heating homes already, but it's designed to be a modular design and sustainable development in mind, so it's able to grow further in the future. If we look at numbers, currently what I can give you from public sources is that district heating production capacity is 4.5 megawatts in the first stage, of which 3.5 is waste heat and 1 megawatt is the electricity used by the heat pumps here on site on this case, because it's outside of, for example, the district cooling network. The annual production here is close to 40 gigawatt hours, or equivalent to around 10 million showers. And if the data center grows to its full size, which we hope to achieve in the future, it will raise the production capacity approximately to 25 megawatts, or resulting in annual production of over 200 gigawatt hours. For a comparison, these numbers, Helsinki's district heating network consumes heat at roughly 1100 megawatts during 0-degree weather. Right now, it's a very sunny and beautiful day here, and it's still only 8 degrees outside. So long into the spring, we will need a lot of heat. And we have other ones, but don't have the numbers to give you, and hopefully a lot of open opportunities in the horizon for even bigger fish. Moving on to a smaller case, this is one of the food industry ones. So any refrigeration, packaging, roasteries, or other food production industries is a very good example of a smaller scale but useful waste heat utilization that this time we offered a solution to as well here. Then if we shift to the production facilities using cooling and waste heat from wastewater. Heat pumps located under Esplanadi Park are in the very center of Helsinki. They're 50 meters below Esplanadi Park, producing district heating and cooling to the area around, and also there's a cooling storage of 25 million liters, capable of cooling over 35 parliament houses of Finland if necessary. And our pride and joy, Katrivalas heat pump plant, it's the largest heat pump plant in the world that is producing both heating and cooling. The numbers are 160 megawatt of heat and 100 megawatt of cooling as of 2023, with the latest additional 7th heat pump here. Located underneath Katrivala Park, where it gets its name, and the park actually gets its name from a Finnish poet from the early 1900s. All of the heat pumps are powered by emissions-free electricity, so therefore they do not generate any carbon dioxide emissions. And the share of energy source for these heat pumps is 80% from the wastewater heat source and rest from the district cooling. But the district cooling share is rising annually since there's more and more available in that network, especially during the colder months. The waste heat temperature for the wastewater is around 10 degrees and the district cooling around 16 degrees. So more and more on the district cooling network means better efficiencies, better capacities. So we're ready for that when the time comes. And that's not all. There's also one Eironanta heat pump plant under construction to be completed in 2025 that is utilizing the rest of the energy left in the wastewater already utilized by Katrivala. That means that after this, basically all the wastewater heat available in the city of Helsinki will be used to produce district heating, like Andreas showed in the first one. That is the largest share. So next ones are around the waste heat from data centers and district cooling networks or any kind of waste heat to be put into cooling networks. Also, the district heating capacity of this plant is around 90 megawatts with the cooling output of 60 megawatts and producing first years around 300 gigawatt hours of heat. And the quickest ones of you have already calculated that this has a capacity to produce a lot more if there's only more energy source available. So basically more heat into the cooling network, more waste heat, especially during the colder months, which of course would mean more waste heat, more production, more and better, higher efficiencies, which means a more competitive district heating price because we still have to compete against other sources of energy. And in addition to these three major waste heat pumps, there's a lot of like environmental source heat pumps on the way or additional ones. And what to do with all that possibly excess energy during the summer times? The seasonal storage is what we're currently constructing. The first one in Finland, a cavern solution that actually was completed last autumn, but we don't yet have the full knowledge of the capacity numbers as we did not get to fill it up with as warm seawater as we would have wanted. And we are considering how much we can use the waste heat around this local district cooling network to increase the temperature and therefore the capacity, energy capacity of the storage facility, because it is seawater, so there's some biomechanics going on and microbiome life. And as a just final remark, green flexibility is part of our strategy, and here you can see what that entails. And what I would consider to show you is that the data centers are in the very center with the digitalization part of this. And I see waste as a value here, and high energy intensive industry and digitalization and the network, the flexible smart heating network are enablers of each other when it comes to this. Thank you. I tried to be brief.
Thank you very much, Jere. Yes, as you told for this presentation, as you told, we are running a little bit late. So I will go straight to our Q&A section. And I would like to ask the first question that we have in the chat to Andras, if you are here. There is a question for you about the EPBD that from 2040, individual fossil fuel boiler will be phased out completely. And he asks what will happen with centralized fossil fuel boilers in building. They can still be in operation. Are there any phase-out mechanisms established already, for example, subsidies for building installation to centralize the heating supply system to connect the building based on individual boiler to district heating?
And I'm sorry that I didn't reply to this question, but somehow my Teams doesn't allow it. So EPPD states that by 2040, individual fossil fuel boilers have to be phased out, but only for new installations and renovations. So the existing ones can be still used. But EPPD also states that by 2050, the all EU building stock has to be zero emission building, which means that afterwards there shouldn't be any fossil fuel heating system in place. The centralized building systems I would categorize to individual heating systems, not district heating. So I would say that it's also enforced for that, but I'm not familiar with that term in specific. Indeed, the EPPD introduces many subsidy schemes for clean heat installations, but these are mainly dealt with on member state level, and we see that there are many different subsidies in many different member states for different solutions. So that has to be checked on national level.
Thank you. Thank you, Andras, for your answer. We have several questions, so I will go directly to Hugh. If there is also a question for you in the chat about what type of thermal storage do you have used in your project?
Yeah, so both our systems use a buffering for thermal storage systems. For the community energy project, we've got 100,000 cube of thermal storage that we use from the extraction system primarily. I'm not sure if that answers your question, but I'm happy to kind of clarify that further if you need.
Thank you. Thank you very much. We have a lot of questions, so I'm going directly to John this time. For the first question for you is if you have any thought on using heat from decentralized EDGE networks. Lots of talk in Scotland about the potential, for example, at the household scales or at heat a swimming pool.
Yeah, this is an interesting one. I did actually reply to Neil, I believe it was. The issue really is that first of all, edge is not well defined yet. So we keep talking about edge data centers, but I think what we have is metro edge, and they're very large data centers. So they come under the same kind of remit as a standard data center. So, but I think there have been there's been a lot of initiative around using small amount of compute to heat swimming pools, or a small amount of compute to heat homes. And there was a company called Nerdalize, a Dutch company that no longer exists, that was selling IT equipment as a heater. And you turn up the thermostat, and basically you say, I can take more workload. You turn the thermostat down, I don't want workload. That's kind of a distributed edge model. But Carnot exists, which is a French company that's doing something very similar. And of course, in the UK, I think there's been a lot of hype around using a small amount of IT to heat swimming pools. The main problem I see with that is that it's okay to continually, because swimming pools basically lose heat, and you need to keep topping up the heat. And that's okay with a small amount of IT, you can do that. But as soon as you go through a maintenance cycle and you refill, you actually need quite a lot of heat to heat up the swimming pool to the right temperature before it's in use. And of course, you can't, if you have only a small amount of compute, you can't actually do that. You then have to switch on the gas boiler it's been turned off most of the time, but then the problem is why do you want to maintain that equipment in the loop when you only need to use it a small fraction of the time? It needs some joined up thinking, really. But it's an ongoing topic of conversation at this point. Yeah.
Thank you very much, John. And Jere, for you, there are also several questions, and I'm seeing that you are already answering from them in the chat. There is one more about what are the temperatures of district heating system in Helsinki and of the heat provided by the DC, and also what are the planned and actual temperature of the cities. I don't know if you can give us more information about this.
Yes, well, I did answer them in the chat, but I'll just say it out loud as well to anyone who hasn't read. So it's quite similar to the Luleå ones that John was saying before. Currently, the dimensioning temperature for the peak heat demand is 115 degrees in Helsinki, but we're working on to reduce that as well as the return side to 90 and 40 degrees respectively, and the district cooling network temperatures are 8 to 16 degrees.
Thank you. There is also another question for Andras. I don't know if since you cannot answer in the chat, I will read it for you.
It's the one regarding the wastewater heat decrease.
Mm-hmm.
Yeah, yes.
Sure.
So thank you, Darius, for the question. It's a very technical one, and from policy perspective, we are not really looking into that. But I have some data what we used for our position papers, which says that thermal energy could yield about 5.8 kilowatt of thermal energy for cubic meter, with a result of 5 degrees of Celsius drop in the wastewater temperature. So 5 degrees of Celsius temperature drop wouldn't have a significant impact on the environment and the water ecosystem. And that's already a significant amount of energy being used from the water. I can drop in the Q&A session maybe a link to this study.
Thank you very much. Thank you. We have 3 minutes, so maybe time for a last question for Hugh, if you can answer this. I was wondering, how have you developed the business case for the project with limited customers?
Yeah, I mean, it's been a particular challenge for us because as a regeneration company, we've cleared a large area, so we're creating new development coming along. So our model is largely based on a revenue deficit funded model that allows us to develop that scope over a 20-year business case that we can justify the investment against. And as I mentioned earlier, particularly for us, where we're dealing with fairly sort of standard end users, residential, commercial customers, we're very much focused on pricing mechanisms. As Andres has highlighted in his first slide, just transition is very key. As much as the technical solutions are there, it is the bottom line in terms of that pricing mechanism that we've had to pay particular attention to. It'd be a lot easier if the electrical pricing in the UK was much better than it is, but much more complex systems need to be developed into that business case in order to answer that question, which is not an easy question to answer. And I think we've still to see how that will flow through, but we focus particularly on the pricing mechanisms to address what the expectations are around fuel poverty in particular, in order that the future is not just reflected in what other utility companies are doing, that we need to ensure that those pricing mechanisms are fair and reasonable to the end users across the board.
Thank you for your answer. Thank you all actually for your participation at this webinar and for your action in answering to all the participants in the chat. It's now time to go to the closure of our webinar. So I was just like to remember everyone to follow EHPA on our communication channel to learn more about our next event and activity. And finally, I would really like to thank all the speakers and all the participants who joined us. I hope this webinar gave you interesting and thoughtful input. And I remind you again that all the material of today, of the presentation that has been shared, we will send to you by email in the next day, and as well as the recording of the event. So thank you again. Thank you all the speakers, and I hope you will have a good end of the week.